Hello students, in this video we'll show that if a function is differentiable, then the derivative has to satisfy the intermediate value property. So let's suppose, here's the precise statement, suppose that f is differentiable on the interval a to b closed. Let's suppose that f prime of a is less than a number lambda is less than f prime of b. Then I can find a value, then there is an xc in the interval AB. It's not going to be A or B, it's just going to be open over here. So in the interval AB, open. So, such that f prime of xc is equal to lambda. That's what we like to show, okay? Now, this is an existence proof, so I need to construct something that I show you some result that we know. And so let's think about how we go about proving this. So what we're going to do is the following. So proof, consider g of x, which is this function f of x, and then minus lambda times x, where lambda is given to us, okay? So now, of course, since lambda is a constant and x is a differentiable function, this function g is also differentiable. So clearly, g is differentiable on the closed interval a, b, okay? So let's compute the derivatives. What were the derivatives going to be? So notice now, so compute, so g prime of x is equal to what? G prime of x is equal to f prime of x minus lambda. So now I have two things I can say. Let's say that g prime of a is equal to f prime of a minus lambda, and f prime of a minus lambda is less than 0. So g prime of a is less than 0. And then what's g prime of b? G prime of b is f prime of b minus lambda, but f prime is bigger than lambda, so this is strictly greater than 0, okay? So in other words, the function g is what? At the point a, near a, the function g is decreasing. And near the point b, before the point b, the function g is increasing. So in other words, what the graph looks like, if you want to imagine this, so here's the point a, and here's the point b. At the point a, the function g is going down, so it's decreasing over here. And at the point b over here, the function wants to be going up. Okay, so that's what the sort of the rough sketch of g looks like instantaneously. So what I can say from this is that now I can find points, so hence, this condition implies that there are points x1 that's bigger than a, such that g of x1 is going to be what? Is going to be less than g of a, is less than g of a, okay? And then there's going to be a point x2, which is going to be less than b over here, such that g of x2 is less than g of b, because g is increasing at that point. So in particular, what does this say? There's points inside the interval AB, there's points inside AB, where g of a and g of b are not the absolute minimum value of the function g, right? So now from this, so since g is differentiable, so g is a continuous function, well, g attains its minimum on the set AB. And the minimum is not equal to either a or b, because g of a is bigger than this point g of x1, so g of a cannot be the absolute minimum value. And likewise, g of b cannot be the minimum value because there's a value smaller than it. So actually, it attains its minimum on the interior. So actually, it attains it on AB open, okay? Now, at a point of minimum, what do we know at a point of minimum? So call this minimum value, I'm going to call this minimum. At this minimum, g prime has to be 0. So hence there exists a point xc in AB such that g prime of xc is equal to what? Is equal to 0. Okay? But if g prime of xc is equal to 0, that tells me that f prime of xc is equal to lambda. So in other words, the derivative of a function, if a function is differentiable on an interval, then that derivative has to satisfy the intermediate value property. It doesn't necessarily mean that if you're differentiable, then the derivative is going to be continuous. You're going to have a discontinuity of the second kind, but it has to satisfy this intermediate value property, and that stems from the fact that the minimum has to be attained on the interior, right? So in other words, the only way that the derivative can fail to be continuous is if there's some sort of extreme oscillation, and we've seen examples of that in previous videos. Thank you very much.